We can use the Wronskian to represent solutions in the homogeneous case of our differential equation. Theorem T2 states that if y1 through yn are n solutions on the open interval from a to b of the differential equation, the nth derivative of y plus p1 times the n minus first derivative of y plus dot 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 plus pn times y equals 0, where p1 through pn are continuous functions on the open interval a comma b, then if at some point x naught in the open interval ab the solution satisfied that the Wronskian of y1 through yn at x naught is not equal to 0, then every solution of the homogeneous differential equation on the interval a comma b can be expressed in the form y equals c1 times y1 plus dot 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 plus cn times yn, where c1 through cn are constants. Now, let y1, y2 up to yn be solutions to the homogeneous differential equation. Another way to answer the question, is it true that any solution to the homogeneous differential equation can be represented by c1y1 plus c2y2 plus dot 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 plus cnyn, is by using the concept of linear dependence of functions. So definition 2 defines when functions are linearly dependent or independent. The m functions f1, f2 through fm are said to be linearly dependent on an interval I if at least one of them can be expressed as a linear combination of the others on that interval I. Equivalently, they are linearly dependent if there exist constants c1, c2 through cm, not all 0, such that cf times f1 plus c2 f2 plus dot 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 plus cm fm equals 0 for all x in the interval I. Otherwise, they are said to be linearly independent on I. Let's take a look at some examples concerning linear dependence of functions. So in our first example, we want to show that the functions f1 of x equals e to the power x, the function f2 of x equals e to the power negative 2x, and the function f3 of x equals 3 times e to the power x minus 2 times e to the power negative 2x are linearly dependent on the interval negative infinity to infinity. So what I want to show here is that there exist C1, C2, C3, not all 0, such that C1 times F1 plus C2 times F2 plus C3 times F3 equals 0. So in our case, we want to show that C1 times F1, which is e to the power x, plus C2 times e to the power negative 2x, plus C3 times e to the power, 3 times e to the power 3 times e to the power x minus 2e to the power negative 2x equals 0. Now I can rearrange this some so that I'm going to get all the terms with e to the power x. And what I see is that you get c1 plus 3c3 times e to the power x, and then plus c2 minus 2c3 e to the power negative 2x equals 0. Now, since this has to hold for all x's, we need to have that this is 0 and this is 0. So we get two equations in three unknowns, c1 plus 3c3 equals 0, and then c2 minus 2c3 equals 0. Now, because we only have two equations and three unknowns, we will have more than one solution. So we can actually just pick a value for one of our constants. Now, we can, for instance, set C3 to any value we would like here. Now, I do not want to pick C3 equals 0 because the goal is to find C1, C2, C3 that are not all equal to 0 such that this holds. So I'm going to pick C3 to be equal to 1. Now, note if I were to pick C3 equal to 0, then this part disappears and I'm left with C1 equals 0 and C2 equals 0. So that wouldn't help me. So now, once I pick C3 equal to 1, my system of equations becomes the following. I have C1 plus 3, and then that equals 0, and C2 minus 2 equals 0. And then from that, it follows that C1 equals negative 3, C2 equals 2, and C3 equals 1. That is one solution to this problem. And there are many other solutions as well if we pick if we pick C3 to be another non-zero constant. So that's one solution. Now in the next example, we want to show that the functions f1 of x equals x, f2 of x equals x squared, and f3 of x equals 1 minus 2x squared are linearly independent on the interval from negative infinity to infinity. So one way to go about this is that we're going to assume that we have constants C1 times F1 plus C2 times F2 plus C3 times F3 is equal to 0 for all x in the interval from negative infinity to infinity. In order to show that they're linearly independent, we now need to show that this must imply that C1 and C2 and C3 are all equal to 0. we must show that C1 equals C2 equals C3 equals 0. So let's write this out. C1 times F1, that's C1 times X, plus C2 times F2, so that's C2 times X squared, and then plus C3 times 1 minus X squared equals 0. Okay, now let's rearrange this a little bit. So this is equivalent with C3 times 1, and then plus C1 times X, and then I'm going to have a term with an X squared. I'm going to write C2 minus C3 times X squared equals 0. And remember that this is for all X. Now, in order for this to hold for all X, we need to have that C2 minus C3 equals 0. We need to have that C1 is equal to 0, and we need to know that C3 equals 0. So what we then get is C3 equals 0, C1 equals 0, and then C2 minus C3 equals 0. Now, because C3 is 0, we can plug that into the last equation and we get C2 minus 0 equals 0, and that means C2 equals 0 as well. And so we have shown that C1 equals C2 equals C3, and that equals 0.